So this is the state point 1. Okay, so this is the state point 1 and this is the state point 2, and pressure is remaining constant, so that is why this is the horizontal line, and volume was somewhere here, and now it is being changed to here. That means process is going in this direction, right? So initially if I'll be trying to show, then this be the volume, initial volume we can say, and this is the initial volume, right? So initial volume was 2.5 meter cube, and this is the final volume. This is 0.5 meter cube, right? Okay. So this is how we can draw the pressure versus volume diagram. Okay, and we can obviously calculate the value of work done for the polytropic. Sorry, that is a constant pressure process, right? So we know in this process, if we want to find out to the value of work done, then simply we need to find out to the this area, right? So area under this one to curve, right? This one to curve is simply representing a rectangle where this volume is, this is 2.5 obviously in meter cube, and this volume is 0.5 obviously in meter cube, and this pressure is given to us as 20, and this is in bar, right? So already all these data are given over here. Then in this case it is very much easy to find out the work interaction during this process, right? So here if we be trying to find out this W1 to 2, then that will be equal to P in V minus E, right? Okay, that means this height multiplied by this length we can say, right? So this is P multiplied by V2 minus V1. Okay, so we will be putting all these values over here. This will be 20. So let us try to convert that into Pascal, because it is given in terms of bar, right? So here it is given in terms of bar, so we can convert that into Pascal. So if we'll be doing that, then this will be 20 will be multiplied by 10 raised to the power 5. Okay, so 20 into 10 raised to the power 5. So this will be 10 raised to the power 5 into, so V2 is equal to what? 0.5 minus V1 is 4.5. Okay, so if we'll be trying to find out this difference, so okay, so this will be equal to what? This will be minus 2, right? So 20 into 10 raised to the power 5 into minus 2. So here we can get this is 40, obviously there will be minus, into 10 raised to the power 5, and unit you can say this will be x. And if we'll be converting this joule into kilojoule, then we can write this minus 40 into 10 raised to the power 2, ready? So this will be 10 square, we can write 10 square, and this will be kilovolts. Okay, and we can write it as W12 to W12 can be written as minus 4000 kilojoule. Right? So this is how first answer we found out, that is work interaction during this given process will be equal to minus 4000 kilojoule. Here this negative sign is simply indicating that, so this work is given to the system. That means during compression process definitely we have to supply some work to the particular system, right? So here this negative sign is indicating that. So what it is indicating, that is work, that is this amount of work is given to the system, that is work is given to the system. Okay, so after calculating the value of work, now we have to find out the value of heat interaction, right? And to find out the heat interaction, we have the relations with us, that is your first law of thermodynamics. When uh, the first law of thermodynamics will be applied to a closed system undergoing a process, for that we know this relation, that is Q1 to 2, that is Q1 to 2 that will be equal to del u plus W12, right? So just now we found out the value of W12, and already we are given with this value, right? In your question it is directly given, so we can take this value directly, right? So by using these two data we can find out the heat index. So just try to find out that. So here Q1 to 2 will be equal to del U, so that is given to us as 3500, obviously in terms of kilojoule, and W1 to 2 is plus, and here this will be 4000 negative, right? And if we'll be calculating this, then we'll be getting us minus 500 kilo, right? Again, here is a negative sign, so this negative sign indicating what? It is indicating that heat is getting rejected from the system, right? So heat is rejected from the system. Okay, so this is how we found out two answers till now. Now we have to find out the value of change in enthalpy, right? So we have to find out the change in enthalpy. So how to find out that? So enthalpy can be found out simply by using this relation. We know what? We know that this is H, right? So H equal to U plus PV. So we know this relation, right? And here it will be trying to find out the differential, that means change in enthalpy. Then we have to take the differentiation of this one. So it will be doing that. dH can be written as du plus P into dV. That means keeping pressure constant, we are derivating or taking the differentiation of volume. Again we have to keep volume constant and take the differentiation of P, right? So this is the value of dH for any process, right? Now what are the process occurring in this case? So what is the process? So in this case process is simply your isobaric. That means in this case pressure is remaining constant, right? So if pressure is remaining constant, then simply we can say this term will be equal to 0. Okay, I think we can say it, right? That means there is no change in pressure. That is how we can say VdP will be equal to 0, right? Now already we know this value du and this value, that is PdV, right? Because this W12, this was simply your PdV, right? So already we have calculated this value, right? And this value we calculated over here, this is as minus 500 kilo, right? So dH value will be also minus 500 kilo. Okay, so in this case we can see one thing, that the heat interactions during this process will be equal to the change in enthalpy, right? So heat interaction during which process we can say? During the constant pressure process, right? So during constant pressure process the heat interactions will be equal to the change in enthalpy. So we can conclude that from here. So let me write that during pressure constant process Q12 will be equal to dH, or we can say del H, right? So change in enthalpy will be equal to net heat interaction during this constant pressure process. Okay, so already we have calculated three data. Now we need to find out the value of this. Okay, so up to this I think there is no issue. Let us move further and try to find out the value of CP. Okay. So I think CP, this is the specific heat at constant pressure. Okay, so to find out the CP we have two relations with us, right? I think try to remember. Okay, try to remember what are the relations related to CP. So do we know this relation? Let us check. Do we know Cp minus Cv equal to R? I think you can remember it. Cp minus Cv equal to R. So we know this relation. Okay. Another relation we know, that is Cp by Cv is equal to gamma. Right. So this is also right. So here this gamma. So this is gamma is the polytropic index. That means this relation can be valid, or this relation can be useful if the process will be the polytropic, right? So if the process is not polytropic, then this relation cannot be useful, right? So we are not going to use this relation over here, right? Now let us look at this relation. So if we want to find out the value of Cp, then we should know the value of Cp and we should know the value of R, right? Where R is the characteristic gas constant, which will be different for different gases, right? So here there is some different gas for which R value is unknown for us. Similarly, Cv value is also unknown for us. That means in these three cases, or the in this particular equation, all these three are unknown, right? And if we want to find out the value of any one, that means we should know other two values. Okay, I hope how to solve and how to approach this clear. Okay, so now by any means, if we can find out the value of Cp and R, then definitely we can find out the value of Cp. Okay, so now let us try to see how can we find out the value of Cp. Okay, Cp and R obviously. Okay, so now we know the value of dE, right? So that is given to us. So let me write that over here. That is del U. It is given to us as 3500 kilojoule. Okay, and can I write this del U? It is del U as M Cv and dt. Can this be written? Try to record, right? So del U can be written as LCV dt. There is no issue. Okay. And from here, if we will be looking into this particular equation, then del U value is given to us, and M is also given to us, and dt, that is the temperature change during this particular process, that is also given to us, right? Okay. So from here, can we find out the value of C? Definitely, we can calculate that. Okay. So let us try to find out the value of Cv from here. Okay, so Cv can be calculated as Cv will be equal to del U, that is 350 divided by M. So M, I think it was given 20 kg, right? So this is 20 into dT. So dT, that will be final temperature minus initial temperature. So final temperature was your 140 degree centigrade and the initial temperature was your 20 degree centigrade, right? So if we'll be taking the difference, then I can write this is 120 degrees centigrade, right? Okay. So if we'll be doing this calculation, already I have done that calculation. So let me check that particular answer. So we can find this answer as 1.458 kilojoule per kg, right? So you can find this answer of same, right? So we have to find out the value of R. So where from we can find out the value of R. So let us see the given data. What are the given data for us? So here, if we'll be looking into this data, here V1 is given, right? P1 and P2 also given, and T1 is given. Okay, so P1, P1, T1 is given. Again, we know the value of this R, right? So sorry, we know the value of this M. So M is given, V1 is given, P1 is given, and T1 is given, and M is also given. So we can assume that this particular gas is ideal gas. By assuming that, we can use the ideal gas equation. And if we can use the ideal gas equation, then simply I can write that P1 P1 equal to P1 T1. Can we write that? Obviously, we can, right? So I can write P1 P1 equal to MRT1. Okay. So in this equation, P1 known, P1 known, M is known, T1 is also known. So from here we can find out the value of R. Right? So let us try to find out that. So R will be equal to P1. So this was given 20 bar. So let us convert that into kilopascal, right? So it will be converting that. Okay, so let us make it Pascal, then we can do the conversion. So 20 will be converting into Pascal, then 10 to the power 5 Newton. Okay, and V1 it was 2.5 meter cube. Okay, then M, this is 20, and your T1 was 20 degrees centigrade plus 273 is 293 Kelvin. Okay, so you can do this calculation, and after doing this calculation you will be getting the answer as 853. Obviously it will be in terms of joule per kg Kelvin, right? And so let me write that, joule per kg Kelvin. And if you'll be making it into kilojoule per kg Kelvin, then we can write 0.853, and this will be in terms of kilojoule per kg Kelvin. Okay, so now uh, the we are having with the values of Cb. Then simply by putting these values in this particular equation, we can find out the value of C, right? So what is the value of Cp? So Cp can be now written as, so Cp can be written as R plus Cb. Okay, and R is equal to what? This is your 0.853 plus your Cb, that is equal to 1.458. Okay, and if we'll be adding these two, then you can find out the answer nearly equal to 2.3 kilojoule per kg, right? So this is how you can find out all these values. So by simply using the equation of your work interaction, you can find out the value of work. This is 4000 kilojoule. So this is the value of the work. And after finding the values of work, applying the first law of thermodynamics, you can find out the value of heat interaction. That will be equal to minus 500 kilojoule. And now this is the equation for your enthalpy, and this is equal to 2 plus Pb. Taking the differentiation, again you are getting the same equation, and from here you can find out the value of enthalpy change. From here you can conclude something, that for pressure constant process, your heat interaction will be equal to change in, right? Now after that we have to find out the value of Cp series. And to calculate the value of Cp and Cv, we have two relations with us, right? One is your Cp minus Cv equal to what? Another one is your Cp minus Cp by Cv, that is right? So this relation will be valid for the process if this is an adiabatic process. So if any process is adiabatic, then can for that we can use this relation, right? So we cannot use this relation because our process is not an adiabatic process. This is a constant pressure process. So we are not going to use this process or this relation. Now in this relation, if we want to find out the value of Cp, then we should know the value of Cp. So now we have to find out the Cp value and R value, and we know the value of that is the relation for d or del u, that will be equal to m Cv dt. So here all these things are known to us. So from here we can find out the value of Cv. So we found out this one. Then from the ideal gas equation, P1 V1 can be written as MRT1, and from here again we found out the value of R. And this is something like this, right? And from here finally found out the value of Cp, that is this. I hope the solution was understandable. So try to solve as many questions as you can. Okay, thank you for listening.